So this is really an attempt to try to stimulate some thought in the room, looking at collaboration and trying to kind of present a problem that hopefully you can bring some good ideas towards, because we need them. Very briefly, so I'm at the University of Texas at Austin. Our research program really focuses on three main areas of research activity: information sources, not just from physical sensors, but from humans, and I'll get into that here in a little bit. Behaviors of systems, systems of sensors, but also orbital dynamical systems. And then, okay, so things are behaving a certain way in space, and you have some information about that, but how do you get knowledge from that? And so this knowledge extraction, quantification, and assessment is the third area of research activity. If you would have to ask me what are the deliverables from the research activity, we're in the business of model development. So developing models of these systems, information and data models, and then decision-making models, and this is where we're don't have a lot of expertise, but we're trying to develop that as we go along. I like to present this Venn diagram because this is a way that we tend to compartmentalize a lot of the problems that we try to tackle. So for people that like set theory, imagine that you have the set of all events and processes that are currently happening in the space domain and have happened and will happen. That set as a whole is unknowable for a variety of reasons. For one, we just don't know everything, and we never will. So it's pretty much that simple. Now, there's a subset, within that entire set, there's a subset of things that we hypothesize and that we model. And then there's also a subset of things that we measure. So one of the things that I stress to my students is, if you want to know something, you have to measure it. And if you want to understand something, you have to predict it. And so the things that we know are things that we hypothesize and we measure. Ultimately, we'd love for these three circles to overlap completely, but that's unobtainium. It's not going to happen, but we strive for that. And some of you in the room may be making fun of me in my skills of PowerPointsmanship and saying, wow, he can't make the circles fit within, why did this happen? I'm going to say that this was purposeful. Why? Well, when it comes to our hypothesized models, our physics, it actually turns out that we have physics that aren't real. We actually hypothesize things that aren't physically happening. We just inferred them from observations. So that's why you see that overextend reality. And then in terms of measured quantities, that overextension is because the truth about all sensors is that all sensors lie. There's no truth sensor. So sensors many times report things that aren't physical either. You have biases, you have spurious information. So that's why you see that. So we like thinking about this Venn diagram and looking at problems in terms of things that we know, things that we know that we don't know. So I may detect some object, I know that I don't know its size or its shape or its material properties. So these are the known unknowns. Through data aggregation, and which is kind of the importance of this talk, we may be able to fuse multiple sets of information and unknowingly have measured some quantity, and we hope that through information fusion, artificial intelligence, machine learning, we can discover those things that we actually measured but we weren't aware that we measured. And then the enigmas are the unknown unknowns. So looking at space traffic management and things that behaviors that enable space traffic management, I kind of put them in two categories: transparency and predictability. We lack openness and accessible space object and event data sharing globally for a variety of reasons, which go beyond the scope of the talk, but we can speak about later at dinner. And then predictability, there's three things I'd like to talk about. One, communication. Especially looking at these so-called mega constellations, if people can, just like for air traffic plans, if people can preemptively share information, tell people, I'm going to maneuver my satellite on this day, at this time, in this way, this is favorable for space traffic management. Cultural competency. Now, one of the things that was brought up earlier briefly by the law panel was things like the United Nations Committee on Peaceful Use of Outer Space. There's these long-term sustainability guidelines that were just adopted. Here's the thing, right? Correct. The UN doesn't put out things that are legally binding, but each nation state can make that law in their own country, right? But then the question is, when people adopt these guidelines, are they going to be adopted the same way? The answer is no. Americans have a specific cultural lens in which they do things in space. The Arabs have a certain lens. The Jewish people have a certain lens. And so, if we can't predict what any given state actor is going to be doing as a result of a specific situation, that compromises long-term sustainability of space. So we have to think about a cultural competency as well to explain object behaviors. Very briefly, most American satellites, guess when they maneuver? Anybody? What days of the week do you think do you see most maneuvers? Tuesdays, Wednesdays, and Thursdays. You don't do it on Fridays because you don't want something bad to happen. You have to explain to your family you can't make it home. You don't want to come in on weekends and holidays, and you certainly don't want to do it the first thing, in the morning when you come off from your weekend. So most American satellites maneuver on Tuesdays, Wednesdays, Thursdays, and Americans thrive on optimization, so they try to do the most optimal maneuvers. That's an American culture expressed as a behavior in space. So it's not just physics. There's human culture that is expressed in space, and so we need to take that into account. And then, of course, my favorite, and probably the reason why most of us are here, is astrodynamics and trying to do the best job that we can in terms of accuracy and precision. Essential ingredients for this space traffic management, the world over has basically said we need some sort of independent way to quantify, monitor, and assess behavior. So, as you know, a couple of weeks ago, India blew up one of their own satellites in low Earth orbit, and basically the folks from India did the kind of the Jedi mind trick. Don't worry about those objects because they're going to re-enter within 40 days. And then people from the US said, do worry about this because we see evidence of things going past the space station. So who in this room has had access to the data to make up your own mind or come to your own conclusion? Raise your hand if you've had the tracking data to write. So the thing is, we still are in this he said, she said kind of world where we're not sharing all this evidence. Strength and transparency comes from an open, accessible architecture that allows a large pool of people to be able to corroborate the evidence, come to their own conclusions, and then compare those conclusions to each other. One of the things that we're actually pursuing are sustainability metrics. I'm in the process of developing what I'm calling a space traffic footprint. So the space traffic footprint is analogous to a carbon footprint. It will not be measured in tons of CO2, but I'm just trying to see if people are awake. That's all. So, it's going to be something that's going to be a composite score, but think of the space traffic footprint as the burden that any object in space poses on the safety and sustainability of anything else. Whenever we get into our vehicle, and as soon as I get into my vehicle and I back up from my driveway to get on the road, I am a burden to other pedestrians and to other drivers. The fact that I exist means that somebody has to take me into account. That is a burden. The fact that any object in space exists is a burden that everybody else has to take into account, whether the object is dead or alive. So we want to establish a composite score, build the space traffic footprint to start quantifying the impact to operations and the environment of all these objects. The European Space Agency talks about orbital capacity. Professor Howell showed kind of these manifolds, and let's call them space highways. And the thing is, any given highway in space can only sustain a certain amount of traffic for safety. Once that capacity is used up, that's it. I got bad news for you. If Elon Musk gets to launch his 12,000 satellites at a specific altitude, Elon has pretty much claimed squatters' rights on a whole shell of orbits. And it's going to be very difficult for somebody to put something else in that. So we should be thinking about this idea of orbital capacity. And then I'm currently working with the European Space Agency, MIT, and Bryce, under the World Economic Forum in developing a space sustainability rating, which will hopefully incentivize sustainable behavior in space, kind of like when you go to a restaurant or a hotel, you get so many stars, so something like that. All right, let's move on. So people talk about space traffic management. I say you can't manage what you don't know what you don't measure. People want to know what normal behavior is in space. Raise your hand if you know what that means. Right. So, problem number one, we don't understand what that even means, what's normalcy. Certainly from a physics perspective, understanding the effects and impacts of the space environment on object behavior, I think that's the ground floor, just if looking at physics. But then beyond that, what does that mean? One of the problems with space situational awareness, think of SSA as just decision-making science for space, is that given a body of evidence, usually multiple hypotheses explain that body of evidence. Oh, my satellite stopped working. Well, what could have led to that? Well, maybe the sun had a hiccup. Maybe a micrometeoroid hit it. Maybe Edward has a satellite that snuck up to me and did something evil. I don't know. I mean, the way you're looking at me, I think maybe that I'm just joking, man. Yeah. All right. So anyway, multiple hypotheses can explain the same body of evidence, and that is not good. What we'd like to get to the point of is one-to-one causal relationships in space. What data, what information do we need to remove as many hypotheses as possible to come to one-to-one causal relationships? That's what we want to be able to do. People are selling persistent monitoring. That doesn't really mean anything. It doesn't exist because you don't have a sensor that sees in all frequencies, and even the multispectral, hyperspectral thing, I think that's good. We need to go in that direction because we need to evaluate as many modalities as possible, but there's no sensor that can detect everything and track everything all the time. All right. This is something that I like to show to make the difference between detection and tracking. So these are all detections from a sensor called the Space Surveillance Telescope, which is now located in Exmouth, Australia. It used to be in New Mexico. It was funded by DARPA, built by MIT Lincoln Laboratory. These are all detections, one night. This is a single night's worth of detections. So the good thing about the Space Surveillance Telescope is that it detects many things. The bad thing about the Space Surveillance Telescope is that it detects many things. So all the detections in black are things that we believe we've detected and we can identify, and everything else is unknown. So every night, that's what this thing produces, is about 50% of the things it detects are untrackable for a variety of reasons. That's a problem. That's background clutter. This is a hazard. This is a threat. Who knows? So this is part of the issue. This is an identity crisis that we need to solve with science, with engineering, and I guess a bit further, when we say, because I've heard people say, oh, well, we need to maximize detectability. Well, we can't just do that because we just end up with a bunch of dots. We need to be able to track things. And tracking is detecting and identifying the object and being able to do that consistently. In an ideal world, every object has a first and last name. We know it, and we know where it's going to go and what it's doing. That's what we'd like to be able to get to. Said yet another way, we have sensor A that is some camera. It opens and shuts the shutter at 3 different times. So the question is, all you get is dots. All you get are detections. Most of the objects up there do not self-report their identity. So then the question is, with a bucket of detections spread over time and space, how do you solve the identity crisis to figure out what's what? That is the area of work that we need to focus upon. What we'd really love to do is start with things that we can measure, back to the you can't know it if you don't measure it, and which combination of measurables gets us specific physical properties of objects, size, shape, all these things. What combination of physical properties gives us insight into functional properties and operational properties of objects, and then can we come up with a taxonomy or a classification scheme, because right now every object in the catalog is modeled as a sphere. So that is not entirely useful. One of the things that we've been developing are ontologies, and it's just kind of a fancy name to say that a way to semantically explain a domain. And so I'm going to give you an example of that. I'm not intending anybody to read any of these things, but basically what we've created is a knowledge graph, and I'll describe to you what that means here. So For instance, we can say that satellite ANIC F1R was manufactured by blank satellite. ANIC F1R has orbital regime GEO. This Galaxy 15 has orbital regime GEO, for instance. So by semantically labeling this graph, the graph itself is knowledge. Somebody could actually read the graph and get knowledge from the graph itself. And the interesting thing about this is that it allows one to amass disparate sources of information, do natural language queries to then discover relationships. Because I could then just say, tell me all the satellites that are in GEO, and I could see that kind of become manifest. So what we've done is we have a three-layered system here. We have raw sources of information on the bottom, two-line elements. We have the Russian JSC Vimpel catalog. We have commercial radar and telescope data. These get mapped into this graph database, the semantic links, the ontologies, and then applications can query that to get information and do analytics and then update this sort of thing. So this is the current system that we have in place. That's the actual website, and you can bring it up on your cell phone if you'd like, or later in the comfort of your own home. But basically what we have is we have over half a dozen independent sources of information that autonomously get mapped into this graph database. When you go to this website, it queries the database to bring up all the orbital information, and I can tell you when you look at these dots based on source, there's a lot of inconsistency, which is part of the awareness that I'm trying to raise. So what are the goals of this? Well, we want to make the space domain transparent and predictable, like I said before. Why? Well, because we want long-term sustainability of space activities. We want to be able to infer hazards and threats to objects in space. I can tell you this right now. People have for long thought that these hazards and threats just come from governments to governments. There's never been a domain of human activity that has been absent malintent. It happens on the oceans, it happens on land, it happens in air. To think that space is just this domain of pure benevolence is naive at best. The thing is, we need to be able to monitor this for checks and balances, and we need to make that body of evidence very transparent and openly accessible so we can all monitor each other's activities for long-term sustainability. The how is, again, we've developed this ontology-based knowledge graph that you can access, at least view these orbital relationships to each other, and we've done this at UT Austin. Right now, again, these sources get culled autonomously. We do have sensor data, radar and telescope data that we process with our own orbit determination software. The orbit determination software is open source. Everything that we do is open source. I told you that we're in the business of building models and putting that out there. And so yeah, we have the actual orbit determination software that processes real measurements on over 1,000 objects daily without a single human in the loop is sitting at this address on GitHub. And you can try that right now. We have a module in Python that lets you simulate data so that you can test it out on your own. So it's all out there for the taking, for the sharing, and we leverage ORCID. So any sort of astrodynamics improvements that we need to do in the actual physics, we try to contribute to the global community and improve ORCID, which is in Java. I think pretty much that's about it. And if there was internet in this room, I'd actually show you AstriaGraph and walk you through it. But somebody told me that you don't have internet in the room, so I guess you do. Can you bring it up? Oh, you can't. You have internet in the room, just not in the computer. Okay. I'm sorry, let me speak more accurately. There's internet in the room, but I'm incapable of showing you the website. So that's it. Thank you very much. You want to use this just so? Well, so people in the back can hear you.
yesterday I actually checked this all this trash in outer space, and it made me think actually for a really long time. And I was thinking, is it possible to go by, for example, some kind of aircraft and collect all the rubbish and go back to the Earth? Is it doable? Like, is my question here in Sydney? You know.
What you propose is expensive, and so one of the reasons for this whole idea of developing the space traffic footprint is if we can do that and assign the footprint to every object, then you can remove the things that have the largest footprint. Then you can say, this one makes sense to remove first, this second, this third, but in the absence of a sustainability metric that provides that insight, I mean, European Space Agency has clean space, they've tested the harpoons and the nets, but what do you go and remove? Like, if you're going to spend money, what are you going to spend the money on? How do you monitor? And many people have said, let's create a space garbage company. How do you monetize cleaning space? And so, again, it's a reason to develop the space traffic footprint is to say, now we can point to these things. And it's a mechanism that actually brings insurance companies to the table, and they can charge premiums based on predicted footprints as well. So. Yes?
But is there any chance by avoiding this rubbish? I mean, to clean this, because what everyone asks is to bring back rubbish to Earth, but what we will do on Earth? There's none. That makes sense.
Yeah, so I mean, if you could, given IADC debris mitigation guidelines, if you could at least have things burn up in the atmosphere, that would be the way to go, right? Certainly, if you're too far away, then that's too expensive. We do have this graveyard orbit near Geo. That makes me very sad because we have zombies in the graveyard. So we have evidence of things being put in the graveyard, except that things being put in the graveyard are actually having children once they've been buried in the graveyard. So we have objects that break up and become more objects, and so they're birthing objects, and those baby objects are now crossing the geobelt and that sort of thing. So that's the graveyard that we currently have is not a long-term solution. Yes.
So, Moriba, you're talking about geo in the graveyard. So, in your Astria modeling and so on, so how far out, as far as the orbital regime is concerned, are you confident that you can do all those detections? Do you reach a maximum radius beyond which, right now, your models are breaking down?
Yeah, great question. I would say probably somewhere in the neighborhood of like 1,000 kilometers above geo is kind of the limit of where we're tracking things. Yeah. And you know, to you and Dan and anybody else that's into kind of dynamical systems theory, if there was a way that we could say, and I know that Dan has looked at this for sure, listen, you know, if you could nudge these objects a little bit over the next century, they will cleanse, that would be ideal. I mean, some people don't want to hear the wait for 100 years, but it's, I think that the solution needs to be a hybrid thing, and that could be one of the things, is nudging things, putting things in a certain location that the dynamical system, these perturbations over time will cleanse some of this population. All right, thank you.